All right, let's go ahead and get started. I want to welcome you back to Unit 4. This is the periodic table, and we're on the third screencast of this unit. So last time we looked at something called the periodic law. And the periodic law simply stated that if you align the elements according to atomic number, moving left to right, top to bottom, that what's going to happen is that the elements that are in a specific column are going to have similar physical and chemical characteristics. In other words, physical and chemical characteristics are occurring periodically on the periodic table. Thus the name, the periodic table, right? So every once in a while, you're going to have elements that are similar in their physical and chemical characteristics. Thus the name, the periodic table. Now, as you move from left to right across the periodic table in any row or period, the size of the atoms generally decreases. They get smaller in size. Now, you'd think that as you move from left to right, the atomic number increases, the atomic radius would increase in size, but it doesn't. It actually decreases. The atomic radius size gets smaller and smaller and smaller as you move from left to right. Well, why? How do you explain this? Well, it's because as you move along a row, there are more and more positively charged protons in the nucleus and more negatively charged electrons in the periphery. And these positive and negative charges attract, meaning that the atoms get smaller and smaller as you move from left to right. Let's diagram that. So let's just say that I have an atom, and this is its nucleus, and it has one and only one proton in that nucleus. Well, obviously, that's going to be hydrogen, right? And I'm going to just draw part of an orbit, right? And in that orbit is one electron. I'll circle that negative charge. So that proton and that electron we know are going to attract one another, right? They're going to attract one another because one is positive and one's negative. So there's this attractive force between the positive and the negative, right? Now, what if we increase the number of protons instead of to 1, from 1, we go to 2. There's going to be 2 protons in the nucleus. So let's put another proton right here, and let me make that a little neater there, and another electron right there. Okay? What's going to happen? Well, what's going to happen is that there's going to be more of an attractive force, right? We're going to increase the attractive force so that you have a second attractive force between that proton and that electron. That's going to have the effect of pulling those electrons closer to the nucleus, right? They're going to be pulled in closer to the nucleus, thus decreasing the atomic radius size, right? Making the atoms smaller. Well, now that begins to make sense, right? Now we begin to understand why, as you move from left to right across the periodic table, that atoms get smaller and smaller and smaller left to right. It doesn't matter what row you're looking at. It doesn't matter what period you're on. The first period, the second period, the third period. It's clear that from this diagram, from this chart, that as you move from left to right, atomic radius size gets smaller and smaller and smaller. And now we begin to understand why, right? But we also see that as you move down a family or a group, say this is the first family or group called the alkali metals. This one's called the alkaline earth metals, but it really doesn't matter which family or group you're looking at. Atoms get bigger and bigger and bigger. Now, why is that? Why do they get smaller as you move left to right, but bigger as you move down a family or a group? Well, it's because more and more protons are being added to the nucleus and more electrons are being added to the periphery, but those electrons are being added into larger and larger main energy levels. And this is known as shielding. Now, let me explain that just a little bit better. If we go down a family or a group, let's take the alkali metals, right? You are adding more and more protons as you go from this element, say, to this element to this element, and this element to this element, and so on. But those electrons are being added into higher and higher and higher main energy levels. They're just further away from the nucleus. The first main energy level is here. It's pretty close to the nucleus. The second one, a little further away. The third, further away, and so forth. So as you're moving down a family or a group, you're adding electrons into higher and higher and higher main energy levels. That's not true as you go along a row. As you go along a row, you're adding electrons into the same energy levels, so there's simply a greater attractive force. But as you move into higher and higher and higher main energy levels, the electrons that are interior to that, or I should say closer to the nucleus than the outermost electrons, are actually shielding that attractive force. So if you look at, for example, this element right here, this element right here has a certain number of electrons in its outermost shell. But the electrons do not feel the full force. I'm talking about this element right there. That the outermost electrons are not feeling the full attractive force because the electrons in the third, second, and first main energy levels are shielding that attractive force. And I could say the same if I go to the sixth main energy level, right? If I look at this main energy level, for example, the electrons in the outermost main energy level, in this case the sixth main energy level, are being shielded by the attractive forces by those of the fifth, fourth, third, second, and first main energy level. Again, we call that shielding, right? We call that effect shielding. So let's kind of summarize here. The atoms get smaller and smaller as you move from left to right across the periodic table, and larger as you move down the periodic table. Now, the periodic law states that when elements are arranged in order of increasing atomic number, as Moseley did in 1913, elements with similar physical and chemical characteristics appear at regular intervals. That's the periodic law. Now, we've talked a little bit about why atoms get smaller as you move left to right and bigger as you move top to bottom, that shielding effect that we talked about. But what happens when atoms gain or lose electrons to become ions? Well, it depends on the ion formed, right? So I want to focus now on the left side of the periodic table, the alkali metals and the alkaline earth metals, let's say. Atoms on the left side of the periodic table tend to lose electrons. Why? Well, they want to be like the previous noble gas, right? They want to have the same electron configuration of the previous noble gas. Well, why? Because that electron configuration is particularly stable. That electron configuration is particularly stable. Well, I'll ask one more time, why is it stable? The answer is that the noble gases have the magic number of electrons in their outer shell, either 2 in the case of helium or 8 in the case of everything else. 8 is the magic number. Everything wants to have 8 electrons in its outer shell, and so I should say atoms on the left side of the periodic table will tend to lose electrons in order to gain that electron configuration of the noble gases. So what happens when they lose those electrons? Well, they become positively charged cations. Cations are positively charged ions as the result of the loss of electrons. For example, let's take sodium. Sodium loses an electron. It becomes the +1 ion. When an atom loses one or more electrons to become a cation, it becomes more positive, right? So on your periodic table, locate sodium. Find sodium on the periodic table, okay? Notice it's one of the alkali metals. It's in that first column. It's one of the alkali metals. Did you find it? All right. So sodium wants to have the same electron configuration as the previous noble gas. What is that electron configuration? Well, let's look at a periodic table. So here's sodium right here. Let me erase this because sodium is covered up. So here we go. So here it is right here, right? So sodium is the 11th element, right? Sodium is the 11th element. It wants to have the same electron configuration as neon, the 10th element. So it's going to jettison, it's going to get rid of one electron, right? It's going to get rid of one electron. And in doing so, it's going to go from a neutral charge to a charge of +1. Now you might say, well, wait a minute. Why would it have a charge of +1 if it's getting rid of something? That's subtraction. Shouldn't it be -1? No. Remember, it's getting rid of something that's negative. It's getting rid of an electron. So when sodium loses that electron, it becomes more positive, right? When sodium loses that electron, it becomes more positive. It gains the same electron configuration, or gets the same electron configuration as the previous noble gas, which is neon, right? That makes it more stable, but it also gives it a charge. Well, what is that charge? Well, the charge is going to be +1. You lost something that was negative, and in doing so, you gained a charge of +1, right? So atoms on the left side of the periodic table, again, tend to lose electrons to be like the previous noble gas. In the case of sodium, again, it wants to have the same electron configuration as neon. Now, they become positively charged cations. For example, when sodium loses electrons, it becomes this +1 ion, Na+1 ion. When an atom loses one or more electrons to become a cation, it becomes more positive, right? So cations are positive. Now let's shift our attention to the other side of the periodic table. Atoms on the right side of the periodic table tend to gain electrons to have the same electron configuration as the next noble gas. So for example, oxygen. Oxygen is 2 columns away from the noble gases, right? So oxygen is not going to want to lose electrons. It's going to want to gain electrons, right? It's going to want to gain, in fact, 2 electrons. So oxygen becomes O minus 2. If I want to write that kind of in a reaction form, I can say this. Oxygen plus 2 electrons becomes the oxygen ion. I can write it -2 or 2 minus. For our purpose, it's the same thing. But it's a superscript, right? It's a superscript. We call negatively charged ions anions. We call negatively charged ions anions. So let's wrap up. On the left side of the periodic table, elements have a tendency to want to get rid of electrons to be like the previous noble gas. When they do that, they become cations, positively charged ions. As we'll learn later, that makes them smaller than the atoms that they came from. The cation is smaller than the atom from which it was derived. As opposed to the right side of the periodic table, say the halogens. These are elements that want to gain electrons in order to be like the next noble gas, right? So they're going to become negatively charged. We call those anions, and as we'll see on the next one, these are going to be bigger than the atoms from which they came. Folks, that'll do it for this one. I'll see you on the next. Thanks. Bye-bye.